So what is Fermat's little theorem good for? So we're going to solve two problems using Fermat's little theorem. And the first problem we're going to solve is the easier one. We're going to prove that if the greatest common divisor of n and p happens to equal 1, then p divides n to the power p minus 1 minus 1. Now let's look at this. So we know that p divides n to the power p minus n. That's Fermat's little theorem. Now if we set this up, we have n to the power of p minus n over p, and we can pull a factor of n out of each of these, and we get n to the power of p minus 1 over p. See, it's the same thing because we just take out a factor of n from the top. But if the greatest common divisor of n and p is 1, then p cannot divide n, so p must divide n to the power of p minus 1, which is exactly what this was stating. Now, the second one that we're going to solve takes a little more effort, but it's not that difficult. So, if we get a piece of paper, we're going to try to prove that 12 divides n squared minus 1 if the greatest common divisor of n and 6 equals 1. So, we have to prove that. So, this is, let's begin by factoring this. So we get n minus 1, n plus 1. And what are the factors of 12? So factors of 12 equals 2 times 2 times 3. So if this divided by 12 is to be a integer, then this has to be able to divide a 2, another 2, and a 3. So let's look at if that's possible. So n minus 1 times n plus 1 over 12 has to equal some integer, correct? So we know that n and 6 have a greatest common divisor of 1. That means that n does not divide 6. That means that n does not divide 2 times 3. So that means that n does not. That means that 2 does not divide n, and 3 does not divide n. So this is very useful information because we can use this to solve this. So let's look at how the numbers are set up. 1, 2, 3, 4, 5, 6, 7. If 2 does not divide a number, that means it's odd. So I'm looking at these guys. Notice that everything surrounding odd numbers does divide 2. It's even. So like this one, this one, this one. So if a number does not divide 2, then its neighbors divide 2. Which means that if 2 does not divide a number, sorry, I'm getting it backwards. So if 2 does not divide n, then 2 definitely divides n minus 1 and n plus 1, its neighbors. So that means that we can pull a factor of 2 out of here and out of here, which is good because then 2 of these requirements are taken care of. But there's still that factor of 3. Now let's notice that for every grouping of 3 numbers, one of them is a factor of 3. In this one it's 3, in this one it's 6. And we don't have to choose that grouping, we can just choose any consecutive 3 numbers. Let's choose these. In that case it's 3. Let's choose these. In that case it's 6. So that means that if you're given 3 numbers, consecutive n minus 1, n, and n plus 1, one of them is a factor, has a factor of 3. Which means that one of these, n minus 1 or n plus 1, one of them will contribute a factor of 3. And given those 2 2's and that 1 3, we can say that 12 does divide that number. And we can further prove that n minus 1, n, and n plus 1, one of them is a factor of 3, and the thing about the 2's, by using Fermat's little theorem to guarantee for sure. So we'll do that in this little box up here. Let's do it in blue. So we know that, let's just restate Fermat's little theorem. P divides n to the power of p minus n. So let's set p as 2. 2 divides n squared minus n. So 2 divides n times n minus 1. So that means that either n or n minus 1 has a factor of 2. And we know that for sure because that means either a number or the number below it has a factor of 2. That's just what we've been saying. And we can apply this to 3's as well. Let's restate the theorem. So p divides n to the power of p minus n, Fermat's little theorem. apply it to 3's, so 3 divides n cubed minus n, so 3 divides n times n squared minus 1. Going down here, I know it's getting messy. 3 divides n minus 1, n plus 1. So that means that 3 divides either a number, 1 minus that number, that number minus 1, or that number plus 1, just like we said.